In this section, we'll try to get a better understanding of the dual formulation by considering a geometric interpretation. Here we have a recall. The optimization problem we are solving is given in this equation. Its Lagrangian is defined as L x alpha beta, like this. Here alpha and beta are Lagrange multipliers. The given problem is equivalent to the minimax problem, minimum over x, maximum over the Lagrange multipliers of the Lagrangian. So it is the same as original problem. So we call it the primal problem. Its dual problem is formulated as the maximum problem by changing the order of minimization and maximization from the primal problem. Okay, this is the dual problem. Now, this portion, okay, now minimization over x of the Lagrangian is called the dual function or Lagrange dual function. So we define by using the G notation, G of alpha and beta, that is the dual function. Now we maximize as in this dual problem, then we can get dual optimum G star, which is always less than or equal to F star, the primal optimum. This is what we have done so far. Now in this section, we'll begin with defining the epigraph of the problem. Now A is collection of RST. Now R is larger than or equal to H, and S is Q of X, and T is a proportion of the original objective function. So sometimes this F graph is called supergraph because we are considering upper part of the objective function in expanded dimensions. Now, F star can be obtained through the minimization, and when R is 0 and S is 0, that means if it is 0 and 0, then 0, 0, t, then it's a kind of t-axis. So F star can be depicted geometrically on the x-axis of the epigraph as a minimum. We'll see details. Okay, here we have the geometric interpretation. F star is the lowest projection of the feasible zone of A to the t-axis. F star, the primal optimum, by definition, can be written in this way. Now this is 0 and 0, and t is a proportion, but among them we try to minimize. T is minimized, then of course this value is minimized, so that it's same as F star. But this one is now R is 0, S is 0, T among the points, and along the now t-axis we try to get minimum, but in fact this one is projection of the feasible zone of A, because X and Q is satisfying the feasibility of the conditions, the primal conditions, so that now among the epigraph you have to find a feasible zone, and then the feasible zone will be projected to the x-axis. That's f star. We'll see along some example what the f star is. Now the Lagrange dual function g of alpha beta is the intersection of the t-axis and hyperplane of normal vector. We'll see here. Now g of alpha beta by definition is this one, the Lagrangian and minimization over x. Now this can be written as now 1 and t is upper portion in the epigraph and that one, so it'll make a t, and now alpha r, that is again upper part of this one. Now beta s, that is upper portion of that one. So among this upper portion we try to minimize, then that must be here g of alpha beta. So we can say that here g of alpha beta is the intersection of t-axis and a hyperplane of normal vector and alpha beta 1. Okay, this is a hyperplane and with a normal vector in RST domain. So this hyperplane is referred to as a non-vertical supporting hyperplane because the third component is non-zero. So that if you consider, for example, a three-dimensional space, so it is a scalar, then alpha beta 1 cannot be here vertical because the third component is always, okay, it's a 1, so that the, okay, normal vector, so always 1, so it's not horizontal, always as a slope, so that the hyperplane cannot be vertical because of this one. So we try to name it a non-vertical supporting hyperplane. Supporting hyperplane means for the epigraph is below of the epigraph. In fact, for the choice of this alpha and beta, that is touching the epigraph and below part, but it never goes to vertical. So we have such name. We'll see figures later on. Now G star, the dual optimum, is the highest intersection of the t-axis and all non-vertical supporting hyperplanes of A. And among this intersection in the maximum, the highest intersection, we already know that G of alpha beta is intersection of the t-axis and a hyperplane. And these hyperplanes, and among them, the maximum possible value, because G star is gotten out of the maximization of this dual function, so that G star is highest intersection. We'll see. Okay, here the strong duality holds if and only if there exists a non-vertical supporting hyperplane of A passing through the t-axis at the point F star. So that is theorem, and once there is a hyperplane passing this point, then it is the strong duality. Okay, let's see examples. We first consider simple equality constrained convex problem. I'm sorry, it's inequality. The minimization over x squared plus 1, now subject to x is larger than or equal to 1. So pictorially we can get this one quite easily. Okay, x squared plus 1. Now x is larger than or equal to 1, that side, this is 1 and that 1, so that this is the value. Of course there is here f is 2, so we can see easily the optimum. Okay, later we'll see a code for just the drawing purpose. Okay, let's begin with the Lagrangian of the problem. The inequality constraint can be written in this way so that the Lagrangian can be defined in this way, which is same as that one. Now if we manipulate in this way, then now x minus half alpha squared and these terms. Okay, so its dual function minimization over x can be obtained when x is same as alpha over 2. So when x is alpha over 2, this term will be 0 and the remaining part is this one. That is Lagrange dual function. Of course, this one can be obtained through the calculus technique. The Lagrangian is differentiated with x because dual function is minimization over the Lagrangian. So we try to make a derivative with respect to 0 and set it 0. So the 2x minus alpha equals 0. Then by solving this equation, we can get x is alpha over 2. That is exactly this one. And now we can get the Lagrange dual function in this way. Okay. Okay. Once you have this one is one of the KKT conditions, or the first order tests, or first order necessary conditions. And for this problem, this condition defines the relationship between the primal variable and the dual variable. And using the KKT condition, now that one defines the dual function and as the function of dual variable, because we got the relation so that x can be eliminated by using the relation. And the dual function is concave, while the Lagrangian is an affine function of alpha. So here, this is concave, is quadratic, along with the coefficients for square term negative, so that the shape of this dual function is given in this way. It is concave. Anyway, we can get this one either with this one or by using the calculus technique as a part of the KKT conditions. Okay, we reached this one for the Lagrange dual function. Now, let's consider epigraph. For the problem, convex problem, is epigraph is defined as this one. The collection of RT, R is upper bound of the inequality constraint, and now that is object function, T is upper portion. So it is a epigraph. This is definition. Now, we want to we want to draw the epigraph. So first we have to find the h. And in order to do that, we try to replace the inequalities with equalities. So from here we have this one, from here we have that one. And then now we try to eliminate x. So t is x squared plus 1. Out of this one, now x is the same as 1 minus r, so that x is replaced by 1 minus r. So we have here. So the epigraph in RT coordinates is given in this way. So once you try to find the edge, this is edge in fact. Now when R is 1, then it has minimum 1. So the 1 and 1, you have a minimum. So that is the epigraph of the problem. Now we have to find the feasible zone. Okay. And first we have to find the feasible. Now that is feasibility, inequality feasibility. And from this one, now that is, okay, R is at edge, R is minus x plus 1. So the minus x plus 1 is non-positive. So R is non-positive. And from this epigraph, left side is the feasible zone of the epigraph. Now we try to project the minimum to t-axis. The minimum possible value is this one. So that is f star. Okay. So here f star is minimum among the epigraph. We try to get the projection from the feasible zone of A, then that is true. So we found here f star equals 2. And in this figure also G star is given. Now we'll try to see now G star. Okay. Now let's consider non-vertical supporting hyperplanes. And for the problem, from the geometric interpretation, G alpha is minimization of alpha r plus t. Let's go to 1154. Okay, 1154. Where are you? Okay, here. That is now this portion. We have now alpha r and t. There's no beta right now. There's no equality constraint, so that is ignored. And alpha r plus t. And minimization. That is same as g of alpha. Right? So that is exactly okay, this equation. And alpha r plus t and minimization over RT in the epigraph is g of alpha. So for some RT, we have this equality. However, g of alpha is given in this way. That is 1157. Okay, let's go back to 1157. G of alpha is obtained as in this equation. So that we set here now G of alpha from this geometric interpretation and G of alpha from earlier by using calculus technique or the minimization over the Lagrangian, we have that. So we try to set it equal. Now we consider this one t, out of this one t, as a function of r. So we write down in this way, then this is now a family of non-overlapping supporting hyperplanes. And by choosing alpha, for each alpha, it will make a different line. So this is a hyperplane in two-dimensional domain, which is a line in the RT coordinates for a fixed alpha. Okay. So in this figure, you can see now the supporting hyperplane, supporting line, when alpha is 0, we have that. It's a slope 0. And once alpha is 2, then this line is a slope minus 2. Okay, look at this equation. Oops. Okay. Now, here, alpha is a slope. Minus alpha is a slope. So alpha is 0. And then that must be 1. T is 1. And alpha is minus 2. Alpha is 2. Then slope minus 2 line in RT coordinates. And along with some intercept, that is exactly this slant line. Okay. Now, there's maximum possible among all these supporting lines. The maximum on t-axis is exactly this point. You can find the tangent line so that it becomes a tangent line, the tangent line at the point. And in this case, the maximum value must be 2 here, G star. So we have this conclusion. F star is the same as G star, and the value is 2. So that's the conclusion. So we have a conclusion, and which means this problem holds the strong duality. Okay. This is code for figuring, and most of the part is for figuring. So this one made the figure you saw. Now we'll go to another example, is non-convex problem. So we try to minimize this fourth order polynomial subject to x is larger than or equal to minus 2. So here, this is original problem. X is right side of a minus 2, and we try to minimize this fourth order polynomial so that the value over there will be the minimum value. You can see it. Now, for this problem, we define Lagrangian exactly same order, same way for the convex problem. We try to go step by step. Now, that is the Lagrangian, and also we define is f equal f. So we recheck that one for the inequality constraint. Now, R is the upper portion, and for the objective function, T is upper portion, and collection of R and T is the f equal f of the problem. And then, for that one, after eliminating the variable x, now here we have such area in the cyan colored region is f equal f, and then now here left hand side will be the feasible zone. So that once you try to project this, the feasible zone to t-axis, then from here you have this value. So the value over there is minus about minus 501.6. So that if you try to make a picture over there more carefully, then this value is about minus 501.6. However, if you try to solve the problem along with the dual formulation, then you can get G star. The G star is now maximum, largest intersection of supporting hyperplanes, in this case line. So among every possible line in the supporting line, now this is the line, and largest intersection, that is G star. Okay, that is way smaller than F star. So for this problem, the strong duality doesn't hold. So that is one example. Earlier, Slater's theorem, we saw that once it is convex problem, then also the feasible zone has at least one interior point. Then now the strong duality holds. But for this example, it's not a convex problem, and then we have different optimum. From the primal problem, we have this value, and from dual problem, we have optimum much smaller than F star. So this is one example for only weak duality. Okay. And graduate student will implement a code to verify this example. But for undergraduate students, the problem is the optional. You can see from the exercise number 5. Okay. This is the end of the section. Thank you.